patterns from data, how we can search for change points, how we can analyze the data within the cloud networks or on IoT devices, or a combination of those. This week we focus on creating machine interoperable descriptions, how actually we can publish data and provide the data in a form which can be interoperable. Different devices from different manufacturers, from different vendors, from different networks can actually exchange data and interact with each other, and how also we can create concepts of actually elevating the data to the level of making them accessible over the web, or what people refer to as Web of Things. There are already some existing standards. There's some work in this area creating different data formats, basically the data formats or service formats, making the IoT data more accessible for machines. In principle, most of these technologies will focus on adding metadata. You will have simple measurements, observation data, and this data description frameworks will add some metadata to make that data more accessible to machines. Let's look at, I took this example from web a while ago. This is like sensory data. Most of the information we access on the web is designed for us to be able to browse, to see, and interpret them. When we look at this information, we can see, okay, this is a temperature data. These are the, I don't know, historical values. Here shows the location of the data. You can add some tags and explain where it is. Here is a Google map, shows, I think it's Slovenia, shows where the data is taken from. And if you look carefully, here is also given the longitude, latitude information. Oh, it's easy to see and easy to find all the relevant metadata. The problem is for machines to be able to actually access this data and to read it, if you look at the source HTML code, is a very complicated task. And the different pages will have different format. For machines accessing this information, it's quite a tedious process. Even if you write scripts to be able to fetch this particular tags from the HTML code, if the layout of the page changes, you need to rewrite your entire code. And imagine if you have multiple providers providing this information in different formats, it will become much more complicated. What semantic technologies, or what we are today trying to discuss, is how we can create some forms of data representation which makes it easier for machines to be able to access data and analyze it. And let's not forget, our initial goal when we started looking at Internet of Things technology was creating machine-to-machine communication. Obviously, in some applications you will have human in the loop, but most of the applications are focusing on machine-to-machine communication. Again, I think I showed this example last week. Let's say if you want to represent a data like this, obviously by looking at it, it's easy to guess. This is the value, temperature value. This shows the unit of measurement, time, longitude and latitude information. Then these are the location data, or what technologies they like to call it, spatial information, space related information. This could be temporal related information. And these are, let's say, value and information. Let's call them thematic, because they will be theme related information. Then in most of the IoT cases, we have three main categories. We have spatial attributes, which are space, location related, temporal attributes. If you have continuous data, you have beginning time, end of time, I don't know, frequency of measurement. You can have different time related attributes, and you have thematic attributes, which related to the domain. What is the unit of measurement, what it measures, what object is connected to this, and so on. Now, how can we make this information more machine readable? Right? We can think of, well, we can add some tags to this information to make them machine readable. When we are talking about tags, we are talking about metadata, adding some data, descriptive data to our data to make it easier for machines to be accessible. Then let's look at this. Can we think of that tags to look something like this? If we create like the most obvious solution for this, we can make those tags something like XML tags. Do I need to explain what XML is? Have you studied XML before? Yeah? Okay. Then if you create a structure like XML, it's more structured, it's easier for machines to read it, and then you can write different parsers, different programs. They can take basically these XML tags and they can use in different programs. Now, if I have 10 different devices, and they're coming from different companies, from different providers, if all of them send information in XML tags, with XML format, and if they use XML tags, I can write programs to be able to separate different parts of data. Actually, the order now doesn't matter. In comma separated, if I change the order, my program needed to be aware of that change of order. In XML, order doesn't matter as long as you look for certain tags. I can query XML. You can process XML in many ways. To start with, XML itself, because it comes in a textual format, is interoperable, is very flexible, is easy to design, and there are lots of well-defined tools to store them. There are XML databases, XML query languages. There are many ways actually to use and process XML. Seems if we use XML, to a large extent, we have solved our problem. Initially, we had some numbers and some metadata. Let's say C, there was a time, location, so on, which was difficult for machines to read and understand. And most of the time, people were creating HTML pages showing this information, which HTML code is not easy for a machine to read and understand. If we change that and we make it XML, it seems like we have solved the problem. Interoperability problem, to a large extent, is solved. Just a quick overview of XML. An XML document will look something like this. For this module, I'm expecting you can read and write something like this. I don't expect you to remember all the XML headings, but in a structured way, you should be able to explain an XML document, how it looks like. You should be able to design a simple XML. Usually it's a hierarchical structure. It comes in a tree format. You have a root element, and you have some basically tags, and it's a well-formed language. Means that all the tags, they close. It's case sensitive. Always remember XML is case sensitive. You can add more attributes to some of your say elements in your XML. You can, for example, describe the data type. You can say what text encoding format you're using, so on. You can make your XML more descriptive. There are forms which you can use to validate your XML. You can use DTDs, data definition types, and XML schema to validate your XML. Means if you're sharing an XML file, or if you're generating an XML file and other people are going to create instances or examples of that XML file, you can define your template. You can say this is the grammar of my XML file, and you can validate against that. This is an example of an XML schema for our temperature data example. Let's look at our temperature data again. This is our temperature data, which has a few values, a few elements, value, unit, time, longitude, latitude. This is an example, this is a sample or instance of that data. Now we can create a grammar for it. And that grammar can be represented using XML schema. Interestingly, XML schema itself is represented in XML. Right? You can say you have an attribute, you can define the name of your attributes, you can say what data format they accept. Basically, you add a template, you add restrictions against your XML, and then you can validate the new documents. That allows you to make sure the documents, the data you're receiving, the documents you're receiving comply to the structure you have created. That again helps if you have large scale, multi-provider data sources. Not only you can create a common format you can share with people, you can also validate their document. You can make sure what they send to you complies to your program. When I say you can write programs to do that, because there are lots of tools, lots of programming libraries. You can check an XML against a schema. You can validate an XML. Basically, you can create structure and you can create rules how that structure should be formed. It's a very simple form. And let's say, if you are sharing now temperature data, if all of you are going to write a program and use this, report the sensor, the temperature sensor data, send it to an application which one of you has written, and that program needs to have one form to be able to accept all this. what do you need to do? You need to create an XML document probably, and you need to agree on that XML document, right? Once you've agreed, you can write one program. It doesn't matter whose mode I get, whose XM1000 sensory data I get, I can integrate that to a database. Right? By doing that, it seems like our interoperability problem, to a large extent, is solved. We are getting closer to create something like HTML, something like a common form for IoT sources to be able to send data, to be able to share data. Correct? The problem starts between these two. What's the difference? Both are correct. Can you tell me this is wrong? Again, I'll go back to the previous one. Temperature measurement, I'm using some tags. This is also temperature measurement, I'm using tags. If let's say we divided you to two groups, one group came up with this structure, the other group came with the previous structure, both of them are correct. The problem was it still is there. Now we cannot exchange data because we are using different vocabularies. Seems like we managed to solve the problem, but the fundamental problem is still there. Because the XML is an interoperable format, but different people can name similar things using different vocabularies. Then we got closer to solve it, but we have to take a step back and look at how we can now solve that vocabulary problem. And then to summarize, in XML, we have sort of like some semantic form. We can add metadata, we can explain, we can describe our documents. However, XML still lacks a semantic model. When I say semantic model, it still doesn't provide any details of actually how these concepts are related. Most of the XML data is a hierarchical structure. You have a root element, and then you have basically parent-child relationships. You have a root element, you say this is a measurement, and then you would say this is the value, this is unit, and so on. Look at this document again. The relationship between in the structure of your document is mainly parent-child relationship. It doesn't say like how actually these different parameters are related to each other or could be related to other parts of your document. But at the same time, doesn't provide any commitments on the vocabulary we use. Who can say, if I call temperature, temperature, or you call it in a different language, temperature, someone calls it T, someone calls it temperature, all of them can be validated, can be valid documents, can be correct XML documents. Then in summary, XML is good to provide a very first layer of interoperability, but when it comes to actually describing complex models, describing different parameters of a model, and describing the relationship between different concepts, there seem to be some limitations with XML. Internet of Things or this domain is not the first domain had this problem. This problem is, has been around for a while, and even information on the web designers at early stages of the web, they realized most of the web content, HTML content, is designed in a way which machines can read and render the pages, but for human users to be able to see and interact with the pages, but machines themselves, they struggle to understand the content of the HTML pages. Let's say, if you look at my homepage in university, it's easy to find my name, my email address, where I am, where I work, what area I work. But if you ask a computer program to start parsing that page, first of all, finding all this information from HTML. Are you all familiar with HTML when I use HTML examples, HTML tags and HTML? I'm assuming you have a basic understanding of how HTML pages are organized, but if you don't, HTML uses tags. And for example, if you want to show a text in bold, you will use B and B, and anything you write here will be bold. Most of the HTML tags are designed to say how the information should be displayed. HTML is mainly a presentation format. It's not designed to describe the content of the pages. But often when you're working in data-driven systems, when you're working on trying to get the data out of the content you have, you need some tags to say, you are not interested whether this is going to be shown in bold or blue or black. You are interested to know this is an email address. This is, I don't know, a temperature measurement. These are type of things HTML or any other display formats they don't provide. They describe how to show the content, but they don't say much about the content itself. Now, the web technologies around early 2000 started looking at some solutions, which they called it semantic web, to look at how you can create more structured documents. Not only you can say how those documents should be shown, how it should be explained, but also you can create some descriptions about the content of the pages. Tim Berners-Lee, who invented the web himself, around 2001, he published an article with his colleagues. They described this concept and they called it the semantic web. And most of the concepts behind the semantic web is focused on knowledge engineering, creating structured documents on the web, which makes it easier for machines to read, understand, and to be able to link different data sources on different parts of the web to each other. One of the, this is one of them, not the only solution, but one of the solutions for describing the documents or describing the content on the web is a format, it's a sort of a recommendation, sort of a standard. When I say sort of, because W3C has recommendations, doesn't have like really standard as such. One of the W3C recommendations is RDF for describing the basically web content. RDF stands for Resource Description Framework, and the key difference between RDF and something like XML is RDF type of forms not only describe the metadata about your data description, they change the tree structure to graph models. Let's say if I had a temperature measurement, in HTML, I could say this temperature has some properties. Those properties could be location, could be value, could be, I don't know, unit. In RDF tries to make this relationship between these two concepts more meaningful, adds a label to these relationships. What happens is how you describe your content in terms of how one piece of content is related to something else or how different parts of your information are related to each other also have descriptions, and you can then later on use those descriptions to write more programs to be able to analyze that content, to be able to link those contents from one source to another. I'll show you an example and become clear what I mean by having labeled contents. But you are changing this tree structure, which you had parent-child relationship, to a graph model. And once you have graph model, you can also link across different documents. You can, for example, link a sensory measurement from temperature now to a description of a room. It's not just now like two tree structures, now you have graph, you can basically interlink between different documents. Again, if you're more advanced XML user, you probably have noticed in XML it's very difficult to link across different to the XML documents. There are some solutions for it, but RDF is designed in principle to create links between different pieces of content and to be able to create meaningful relationships. Everything in RDF is described as a triple. Each triple will have an object, a subject, and a property which links this two together. When I say triple, then you will have always pairs of object, property, subject. Let's say an object could be a temperature value. Let's say a temperature sensor. This could be an object. A property could be has value. And a subject could be the measurement value. For example, my sensor could be, let's say, device AB01, has value and that value could be 20. Now I can make this description more complex. I can say has unit of measurement, has unit, and I say unit is Celsius, and so on. I can make this relationships now how different my data is connected to different parts of its properties. I can make those properties to have labels and to have meaningful relationships. Once you start doing this, then you can write programs. Now go and find all the sensors which they have has location, and the location is equivalent to AP01, for example. Then you can start searching for information, retrieving your information based on meaningful properties. You can write programs which can link different parts of, find all the temperature information which they have a property of has location. Location is within the area of Guildford, and then finding all the sensory information from that area. You can start searching your information, traversing your information based on a knowledge graph. Different pieces of information get connected to each other. In a very simple form, let's say, again, going back to our measurement example, our measurement example will look something like this. I have a measurement data. In XML, I had my measurement data. This was my measurement. And everything else was just subclass of this, subproperty of it. It was a parent-child relationship. A measurement has, it's not readable at all. Let me write it properly. A measurement in XML would have had unit, would have had value, would have had, I don't know, location, 1 to 8, 1 to 6, would have had this properties. And would have, all of them would have been just parent-child relationship. Here, my measurement value will be described as a graph. Means all the properties I'm going to explain now for my document will have a label. And those labels can carry meanings. And you can describe some conventions how those relationships are going to be defined. You can add, similar to XML, you can say what will be the end target. Here, for example, unit will be a string, longitude will be a double number, latitude will be a double number, I don't know, value is a decimal, and time is a time domain. And if you're wondering what this XSD is, this is the namespace for the standard XML data types. For our discussion, for the sake of our discussion, you can ignore it. It doesn't matter. But if you're interested, this XSD is the namespace. Do I need to explain what namespace is? Yes or no? Okay. That's where you have basically described your vocabulary for that. And these are the standard XML data types. Now that we have moved one step further from XML, one of the key problems, in XML, remember, we had two problems. One is we had this vocabulary commitment. Different people could have come and describe the same thing using different vocabulary. And XML didn't say how different parts of the metadata is linked to my metadata. Everything was parent-child, everything was property of the root element, but didn't say what, based on what relationship those properties are. Again, most of those knowledge embedded in the designer's mind. And when the machines are going to work with it, machines, they don't have that intuition. We relied on human intuition again to say these are the sub-properties of an element, but machines don't have that intuition. We want to be able to embed that into machines, to be able to tell machines why we think this property is related to this document and based on what relationship. Then we have solved the first problem. And the first problem is now we are, well, the second problem, to be fair. The first problem of the vocabularies is still there. The second problem, which was creating meaningful relationship, now we can describe our documents using a labeled relationship. We're able to provide graph structures. Now, take our example again. Look at this structure. Let's call it a schema. This is the abstract form. I can create instances, right? This is an instance of the same model. Now I can create 1,001 million measurements according to that model. And I can go and say now, go and find all the measurements which they have a latitude, and the latitude value is closer to this one. I can go and retrieve all of them. Can I? you can now write programs to say, go and find all the data which comes from this latitude, comes from this combination of this latitude and longitude. Look at the data, see if it has unit, and if the unit was Fahrenheit, use this formula to convert it to Celsius. Now you can write programs which you can add more rules based on the meaningful relationships, right? Can I give, before talking more about the structure, these are all graphical notations. In practice, RDF can be expressed itself as an XML document. Then there are different ways of serializing RDF. One way of serializing RDF is using XML serialization. There are other formats of RDF serialization, but take for now, you can use XML. And I have oversimplified this document. I didn't show the namespaces and headings here. It's just a very simple way of showing RDF. But in practice, RDF will have like namespaces, headers, and other information as well. Right. Very much looks like our initial XML document with a difference. The difference is here, those labels, those properties we have described for the document comes based on some intuitive modeling, based on some models we have decided, and those labels will carry meaning, will say how different pieces of information are linked and connected to each other, right? Can I add more structure now to my document? Can I take the location? Let's go back again, look at this example. If I'm measuring 1 million, or not 1 million, let's say 10,000 readings, and for every single of them, if my sensor is in the same location, instead of sending this longitude and latitude information every single time, if my sensor doesn't move, can I make my document more structured? Can I say has location and create a location object, right? And then when I create examples, I can create now thousands of examples which they will have different measurement data, but they will, their location always be location 0, 1, 2, 6. Can you do that? And now you see, when you create this labeled descriptions, when you create more structured descriptions to say how different pieces of information are connected, and then you create sort of, you can see they are moving towards more object-oriented description. These are like, exactly like object-oriented. I created an instance of a location, and I gave the location 0, 2, 6. Now if I have 10,000 measurements from that location, I don't need to add that longitude, latitude data 10,000 times. I will just, for every new measurement, I will say has location, and I link it back to that location object. If my sensor's location moved from 1 to 6 to location 1 to 7, the new measurements will be linked to the new documents. You are creating basically a concept of sort of linked data. Your data can get linked to different other metadata or other data based on meaningful properties. That's basically, in principle, that's entire concept this lecture is trying to capture. If you find a solution, which we already explaining it, to be able to add metadata, make that metadata more structured, make that metadata more labeled, then you can write more structured ways of analyzing and describing your data. We are getting more closer to interoperability. Now, if we have different providers, they agree to describe their documents according to this model, and they create structured documents. Now we have more or less, we have basically met all the key requirements for interoperability. We have machine readable descriptions because they will be described in XML or other forms which we have different tools and libraries to read them. Then they are machine readable. They are more structured. They can link to different pieces of information, and their links are meaningful. More or less, we have solved the interoperability problem. Now, if you're all writing programs to collect temperature data using your XML nodes, if we agree on a model like this, and you create structured RDF descriptions, If you're sending data from different locations, if different people are in the same location, I can still find the relevant the sensory measurements from the same location. I can search for, find all the data measurements which they are sending the data using, I don't know, a unit of measurement in Celsius, all those sending their measurements in Fahrenheit, all of them which they have measurements in a certain time of the day. You can make it more complex. You can say has a start time, has end time, has a frequency. You can add more properties. And then I can write different programs to be able to extract different parts of information from what you're measuring. But there is a fundamental problem we still haven't solved. And that fundamental problem is still you can use different vocabularies. Back to square one. In XML, we moved on from XML because in XML, different people, you could use the same tag, different tags to describe the same concept. Here, it's more complex model, but still the fundamental problem is there. Who will stop you to call this measurement M or ME or whatever you like to call it? Still the fundamental problem is there. That's why interoperability becomes a big problem in Internet of Things, because most of these devices are programmable, they are still in their early stages of their development, and people will program them with different formats. Even they are using machine interpretable data, they are still not machine understandable. Still you are relying on assuming people are going to use the same conventions you're assuming to use. If they say instead of has longitude, they say has long, is correct, but if you have written a program which is only sensitive to has longitude and has latitude, won't be able to detect them. Then the fundamental problem is still there. Just to summarize quickly from RDF, in RDF we have triples. We have triples of object and subject which are linked with a property. Then everything is a triple. All the strippers, they are using a URI. Means everything is a URI. Everything you explain has a namespace and has a unique identifier. That also helps with the naming and identification in many cases. And this objects could be like sensors, actuators, could be a road, could be this room has temperature and the temperature is measured by a sensor and so on. You can create different models to explain that. All these properties themselves, also they have a URI. I have added, for example, an example of this. And that means the properties themselves can be unique. You can create your own namespace and you can define your property, or you get the property from somewhere predefined. But whatever you say as a property itself has a URI. It means that property is somewhere well described, has a namespace. It's already, you have defined your vocabulary and you can use it. RDF has a query language. We are not covering this. This is covered in a different module next semester, but there's a query language for basically querying and questioning RDF documents. It's called Sparkle. And it's a logical language because RDF is designed based on principles of logic, description logic. You have triples, all the triples, they have meanings, and then you can write, I don't know, if let's say A was B and B was C, you can extract A dot C. Let's say if temperature was from a room and the room was located in Austin Piers, then this temperature is from Austin Piers. You can write programs like this, right? You can write basically inferencing and you can extract information. Sparkle will be the query language, won't be the reasoning. This will be the query language. But in principle, because you have now triples and you have all these triplets, they have meaningful relationships, you can write reasoning code to extract information. Back to our fundamental problem. And the fundamental problem is the vocabulary. Still different people can use different vocabulary to explain the same thing. At the spoken languages around the world, we can create even more inconsistency because who says you cannot explain the same concept in a different language? I mean, still, you will have the inconsistency problem even if you use the same terminology but in different languages. One way of solving this, people have come up with a term called ontology. Have you studied ontologies before? Are you familiar with the concept of ontology? Okay, ontology, the term ontology comes from philosophy. In philosophy, there is one ontology, and that's basically the domain of discussing and describing existences in the universe. And for a long time, I think if you wrote in Microsoft Word ontologies, you try to make it plural, Microsoft Word used to show an error, say, oh, you can't, there is only one ontology. But computer scientists, they hijacked that from philosophers, and they created different ontologies. They said not only we have more than one, we have infinite number of ontologies. You can create ontology to describe universities, you can create ontology to describe sensors, to describe a power plant, you can have ontologies to describe anything you want. But the fundamental concept is the same. An ontology is a set of concepts and relationships which describes the important key concepts in a domain. Domain, let's say in a very simple form, because when we try to describe different concepts in a domain, we will use different vocabularies. An ontology will try to come up with a common language for us. We'll try to create sort of a standardized vocabulary to describe that domain. Let's say if you're modeling our sensors to measure temperature and light data, which you have in your sensors in the lab experiments, instead of each of us, we are using different vocabulary. We try to agree on an ontology. That ontology will be our common language to describe our measurements from that particular domain. And that concept has been around in semantic web for a while, and there are lots of ontologies also designed for Internet of Things. In principle, what they try to do, they try to formally describe the important concepts and the relationship in a domain. Let's say if we have now a mobile sensor, and this mobile sensor has, mobile device, and that mobile device has sensor, let's agree how we are going to describe that. And that agreed terminology and the relationship between those terms will be described as an ontology. Let's say in a university setting, the important concepts will be students, staff, the modules, the lecture theaters, departments. And to create an ontology, we'll say, these are the important concepts we have, and we describe how these concepts are related. For example, we will say, I don't know, a department offers some modules, and we'll describe offers. And let's say if all the universities in the UK, they agreed on how they're describing their program and they publish this data somewhere on the web, doesn't matter, you can write a program to find all the electronic related programs, modules based on the relationships, if you know everyone is going to use the same vocabulary. Then an ontology is part of designing an ontology is knowledge engineering. Part of it is doing standardization, getting people to agree on the terminology. If you're going to design an ontology for our module here, for the temperature, light, and temperature data, we need to make sure you all come and sit here, we discuss, and we agree from now on, everyone for temperature is going to use the terminology temp. And as long as you're using temp, then we know that that's the temperature data. If you're going to describe the unit of measurement for your temperature data, let's say I call it has unit. And then we agree, we all call it, we're going to call it has unit, we're basically moving towards creating an ontology. Now, let's do a very simple practice for actually a temperature sensor. If you're going to create a sensor, temperature sensor, let's say ontology, what terms do we have? Well, first we have the sensor itself. Yes. Okay, we have unit. What else do we have? Let me write them here and then we create the graph. It'll be easier. What else we have? Important concepts in this domain. Location. Measurement itself. What else would be the important topics here? Time. Anything else you can think of? Okay, let's start with this and see where we get. Now, the first step in designing an ontology is agreeing on the terminology. What should we call our sensor? Shall I call it sensor? Shall I call it device? What should I call it? I'll start the first one. Let's call it a device? Can I say sensor is a device? Because I can have another concept here, actuator, later on if I want to create another model. An actuator could be also as a device, right? And now I can say, go and find all the devices in my platform. You'll find all the devices in a certain location. You can expand your model. A sensor has a measurement. Can I say has a measurement? Can I say that measurement has unit? I'll call it has measurement. And that would be unit. And can I say that unit has value, which will be Celsius, for example? Yeah. You can add further descriptions. This measurement has location. And location itself could be an object. And the location could have longitude and latitude. Can I say measurement has time? And this time I just make it a value. When I show rectangle boxes means they are values. When I show ellipse means they are objects. And this is time value. So if we take this model and we represent it in XML, and if you all agree on the terminology, doesn't matter whose data now I take, I can write a web service which can collect data from your sensor measurements, and doesn't matter who you provides that data, who has, actually doesn't matter what program, how you have written your program, as long as you send the correct measurements, I can get that and integrate it into my platform. So.
With the sensor is a device, then wouldn't the hour got to be all the way from sensor to device? If the sensor is a device.
Sorry, that's correct. I should have put the relation in a different way. Thank you. That's correct. Also depends how you define this relationship. Could I have a reverse relationship here also? If you want to go from device to sensor, what do you call it? You can just also have a reverse relationship because they are all conventional how we describe it. Device has type, for example. Depends how you describe the relationship, but your point was correct. Now an ontology is these concepts and the relationships and agreeing on the terminology. Part of it is the knowledge engineering of it. It's actually how you design an ontology which describes all the concepts, all the properties you have. The second step is how you represent it. Like if you use RDF, you can represent that using XML serialization or different forms. And then you can create tools to be able to describe that. And the most important part is creating something which becomes more universal, getting all the key partners or key parties in that to agree how they're going to send this information. If you're writing, let's say, an Internet of Things module assignment, and we want to make sure everyone sends their data in a common format, we just need all of you, 50, 70, how many of you are this semester, to agree on that terminology, or say majority of you agree. The others probably have to follow. But majority of you agree, then we have created an interoperable format. Now, if you're creating an industry solution, you need to look at your suppliers, your data providers, the people who are going to use your data, and to make sure all of them agree on a common format. If you do that, we are addressing that vocabulary problem. Then most of the previous steps can be solved by data engineering, But the last part, which we need to get an agreement on vocabularies, also comes with a little effort of actually talking to the problem owners, talking to people who are actually going to use this data and make sure you agree on terminologies. The part of creating ontologies is creating standards, creating models which are commonly used by other groups as well. One thing I have added, just one slide, RDF provides a very basic form of describing triples if you want to add more restrictions. For example, if you want to say a device can only have two types, can be only actuator and can be a sensor. Like you don't want people go and add TV, I don't know, mobile phones. You want to add restrictions. There is a special language for that. It's called Web Ontology Language, or OWL. Just probably sounds cuter, they've made it OWL, but it stands for Web Ontology Language. And OWL is, again, can be represented in XML, has more logical restrictions. If you're interested in further going and looking at it, not for this module but for yourself, OWL is described based on first order logic. It's a logical language, it's a description logic, and you can write logical statements in OWL, and you can have reasoning and more descriptions. And obviously in IoT, always you have to remember, any more descriptive formats you add more complexity, and most of your devices will be resource constrained. But that doesn't mean necessarily this needs to be added in the source. You can add it in your cloud networks and use them. For example, you can say the properties are, add property restrictions. You can say those two properties are completely separated from each other. You can say add versioning to your descriptions. You can say two things are equal, and so on. Ontologies are easy to describe. As I said in the beginning, it's difficult to make people interested in. Because if you design your ontology and no one uses it, or people start again using a different vocabulary, back to the square one, we have the interoperability problem. That goes to our earlier discussion why we don't have global IoT networks, because part of it we don't have that common format to be able to describe all the data coming, and also the diversity problem, because we are not just describing text, we are describing different phenomena, different temperature, light from different environments, different domains, and all of them, they will have different characteristics. Having said that, still there are some best practices for designing ontology. If you're attending this module, I would like to be familiar and to follow certain principles in designing your ontologies. The very first step is, in an ontology you need to describe, to be able to understand the domain and to see what are the key concepts in that domain, what key classes, concepts I have in that domain. And then what are the relationship, or how I describe their value, how I describe their relationship, and what would be the limitations I have. That will be your abstract level. You will say I have, departments and I have modules, and these departments offer modules. That will be your abstract level. And then you need to start adding instances. You will say, for example, electronic engineering is a department, offers Internet of Things module. Computer science is a department, offers Internet of Things module. Those will become instances of your abstract concepts. Again, it's an object-oriented concept. You have concepts and classes and individuals, or instances from the classes. There is no there is no correct or wrong way, but there are some certain principles. There are some best practices. Usually it's an iterative process. You will start with first defining the key concepts, defining the relationship, creating your model, creating an instance to see if it's sufficient, add it to your application, and then you start adding more descriptions. Usually the terminology you're using is better to have more meaningful descriptions, because you're creating it for machines, but you want also the human users to be able to read and understand. Nothing stops you to describe temperature as say T has U, and say has U. But if someone who didn't attend this lecture once will read my notes, there's no way to actually understand what we meant here. But when we say temperature has value, and that value is a value, that probably is also easier for human users to read and understand. That will help you for versioning, for basically more collaborative way of designing ontologies. Then a few steps. To design an ontology, determine what is the domain and scope of the model you are designing. Often people, when design ontologies, they look at and create a very complex model. I never forget the first ontology I designed here. The first sensor we had created like a model for describing a sensor as a device, and the properties had 200 properties. I went and created the best model, everything we could think of. We looked at all the data sheets for the sensors we had and added all the complex properties. One thing I hadn't thought about it, actually the problem, why we are designing it and where we for what purpose we are using it. And then I remember one day one of my colleagues walked into my office and said, oh, we have built a test bed. We want to use your interoperability model because we can annotate our data according to your model, and then we can open it up and other researchers can come and use it. And my first question was, how many sensors you've got? And they had around 1,000 sensory devices or sensors. And I thought of 1,000 times 200 properties. I have 200,000 properties to describe, so forget about it. That also led to the second problem. I had actually designed a model without thinking how people are going to annotate according to that model. I had no tools. I had designed a model in Graph, some tools to explain it to myself, to show it, but I didn't have any libraries, any tools to be able to give it to people to be able to use it. I'll talk about it in a minute, but when you're designing also ontologies, it's better to use terminology if they exist before. In a recent project we had, we were working in designing a healthcare IoT test bed. We were working with 10 companies, and they were providing healthcare monitoring devices, and we wanted to create a platform which doesn't matter whose products I'm getting to monitor a patient's blood pressure. As long as they are monitoring blood pressure, monitoring someone's heart rate, I should be able to integrate that in a platform I'm going to make. To do that, we needed to create a common language. We needed to all the 10 companies to agree to send their data according to a common format. That was an ontology, right? We needed an ontology to do that. But we didn't go to create we didn't start at creating all the terms from scratch. It turns out, like in healthcare domain, there is actually an ontology in healthcare domain called, not ontology, sorry, a vocabulary called HL7 or FHIR, FHIR, and there is a terminology called SNOMED. Just writing it here if you're interested in medical applications. If you go to see your GP, if your GP takes your blood pressure and adds it to our system, most of the time that data actually is stored in this country according to this terminology. All is stored because all the NHS systems, they want to be able to interoperable to get their information, be able to share it. When we were designing an ontology for our healthcare application, instead of going and inventing the terminology for ourselves, we went and looked at, can we borrow some of those terminologies from SNOMED and HL7? If you use that, then in future you are compatible with more other data sources. And if designing any ontology in any domain, if you go and work for a company, they wanted you to design a data model, first ask, how have they been explaining and describing and storing their data? Maybe there are some already existing very well-described terminologies, standard models, and you might be able to borrow some of the terminology to extend and create your ontology. Once you have done it, start actually enumerating your important terms and say, what are the key terms I need to design in this ontology? Do I need all the terms? Do I need all that 200 properties? Maybe some of them can be optional. Maybe keep some of them aside and say, this is my core ontology, which has only 5 properties. That's often very useful. Then decide on defining on the classes, class hierarchy, and decide how the relationships are going to be defined. For example, if you have, let's say, you're designing an ontology for university. If you're saying university has department, is it a separate concept? Is it a subclass of a university? What it is, you need to decide, because later on when you're analyzing data or you're writing more descriptive queries to be able to get this data and use them, this will become important. Now, how you link these different properties, again, the properties, the labels themselves need to be meaningful and needs to be, if possible, to come from standard described properties, which makes your analysis of your descriptions easier in the future. And if you need to have some logical expressions. For example, if you have, let's say, a sensor and you want to make sure that sensor only is associated to one location, you can add restrictions. You say only like, in RDF you have very limited features, but in OWL you have more features. You can say, for example, this property can be only enumerated once. Means the sensor can only have one location. It's not a quantum sensor to have two locations at the same time. These restrictions can be added to your ontology description to make sure your data is consistent. Later on, when you use the data, when you're using the descriptions, you can make sure the data you get is already pre-validated. For example, if you're reading someone's body temperature, I don't know, you add some restrictions to say this body temperature can be only between 35 and 42, cannot be -5. And then you already define some restrictions. But most of these restrictions are not in that level. Most of them are logical restrictions. For example, this is can only have one type, or could have like a few types. And then you start adding your instances, because most of the time when you design an ontology, you describe your abstract concepts, and then you start creating samples of it, instances of it. You say, I have a sensor has value, has measurement, and you describe the abstract concepts, and then you say a temperature sensor is a sensor, and you describe the instances. Last year, or a few times in the exam, I have given some description of a domain, saying, actually 1 year I just took the data sheet, the catalog from the XM1000 sensors, and I said, design an ontology to describe these properties for a sensor. If you've been listening for the past hour, it's very simple now to do that. You just need to decide what concepts you have, how you're going to relate them. You describe the abstract concepts, and then you would have created an example to say, now I have XM1000, my XM1000, and that has the sensor, and so on, as a measurement. The ontologies can be described using like RDF, can be used, you can use OWL, you can use RDF XML serialization. RDF has different serialization. In the exam, if you write as triples, you say, for example, measurement has unit C, I'll accept it still. I call them triples. A measurement, I don't know, measurement. A sensor has type, and type is temperature. Usually, if you show it using a graph, showing a triple model of RDF, I'll accept it. And in principle, you don't need to learn how, you need to be able to understand and look at and be able to interpret the RDF syntax, but you don't need to remember all the RDF details. There are tools that will help you to create RDF descriptions. You don't want to read and learn or to create RDF by heart on all the domain spaces. No one needs to do that. Now, there are different other forms of representing interoperable data or creating more descriptive data. I took JSON as an example because it's more popular, and there are lots of examples of JSON in higher level languages, in different programming environments. You can use it. Basically, in JSON, everything is ordered like as attribute value. This comes like pairs of you have a attribute and you have values, and like any other programming data structures, you can create arrays, lists, sequences. But I'll focus on some very simple examples of how you can describe. Let's go back to our sensor description example. When we showed our XML, we walked it through showing it as in RDF, showing it in how you can create models, how you can create it more structured. Now let's see how we can explain it again in JSON. In JSON, you will have, again, a main element you're describing and property value. So I think 1 year I showed one of this, I can't remember which one, and I asked for the other. Probably I alternate every year. I pick one and ask for the other. If you have this JSON data, can you show it in XML? This is an IoT data. But I think I did an XML and I asked for JSON. With the standard JSON, the problem is still we don't have the semantics. Anything we said about XML, the restrictions about XML, parent-child relationship, all the linking different documents, all the vocabulary problem still applies to our standard JSON. Anything we said in XML, which we said as a limitation, JSON will have the same thing. How we add semantic descriptions to JSON, how we add metadata to more descriptive metadata or type of ontological terms to metadata, ontological terms to JSON is a concept called JSON LD or JSON link data. And JSON LD first is 100% compatible with JSON. That means if you have a program which only understands JSON, will actually ignore the rest of the semantic annotations you have added. You won't be able to read them, but will ignore them while still you're compatible. But there are some ways in JSON LD provide some ways to add your metadata description to JSON. In principle, your terminology comes from an ontology. Then instead of saying here you have a sensor, you add the namespace. You can add the namespace, you can add the ontological description. And that means if you're calling it this way, everyone has agreed your sensor name will be called using this terminology, and that's the namespace you have described your ontology. Basically, that's the namespace. And by using that, you're adding more, let's say, interoperable descriptions. If you're saying, for example, I have an API, then you can have, I don't know, URLs. You can say location, it comes from somewhere which you have described that location as a part of an ontology. Then all the terminology can come from an existing vocabulary you have created. Basically the same principles of JSON, only adding some semantic annotations. To make this description, these are very tedious. If you write all this HTTP, blah, blah, all this becomes very tedious in JSON documents. To be able to create something more easier to show and easier to parse, we have a concept called context. Basically, in context, if you add context to your JSON documents, you're adding something like namespace descriptors to your JSON documents. Then if you're saying my context here, for example, is HTTP JSON LD here, instead of repeating it as every single time, then we know all of these concepts, they have a preliminary namespace. It's really like any XML document. It's just a way of creating abbreviation for your document, providing a context saying where this terminology comes from. And instead of having all these namespaces here, repeating them, you just add a context and say where they come from. Yeah. Now, if you add semantic descriptions to IoT data, obviously we are addressing the interoperability problem, especially if we have different providers, like in our healthcare applications, when we created that common ontology using HL7 and FHIR model, and everyone agreed to create that data according to that format, we created some validators on our backend system, and we agreed people will use, let's say, some RESTful interfaces to send their data. But after that, it didn't matter which patient got whose device patients they got. As long as they were sending data using the common language, I could get that data and integrate it into our platform. If you are designing an IoT application for an industrial platform, as long as all your sensor providers or device providers, they agree on the terminology, you can create a data analytics platform which can get the data from those sensors and integrate it. Then it makes it easier for you to get the data and integrate it from different formats. If you're looking for the resources, because you can describe the sensors, the devices themselves in semantic description, then you can write higher level queries to be able to find your resources, find the properties. You can process the data, they're providing it. And in a higher level, you can get the data from different sources and integrate them to make more actionable information from them. A few further notes on designing ontologies. When you're designing it for IoT, you have some further constraints. You need to have something lightweight models. The complex models could be good, but if you're deploying in large scale, if your resources are limited, then you need to create something which is more lightweight. If there are existing concepts, terminology in that domain, it's better to be compatible with the existing terminologies instead of inventing your own terminology. In some cases, you can create, it's better to create a modular ontologies. Instead of like creating everything like in a form which very interlinked to each other, you create a modular description. If I'm interested on the quality of the data, I will add the quality properties. If not, it's easier for me to understand what properties I should put aside, for example, when you're designing your ontology. This is an example of an ontology came from a work at W3C called Semantic Sensor Network Ontology. It's one of the most popular ontologies in describing the sensors and describing their measurements. And if you look at it, they've designed different components. And each component describes, for example, this part only describes a deployment environment. Here describes sensor as a device. If you're describing only your sensor device, what properties you need. Here are the inputs and outputs, for example. This type of modeling, in principle, is the same thing. You describe the same parameters. It's just a good modeling approach, makes everything very modular, and then you can take and add the modules depending on what you need, what area you want to focus. Once you have your data, you have added the semantic annotations. If you use different web technologies, RESTful interfaces, RESTful technologies, last week we discussed CoAP. If you use any of those technologies, make your data available at the web level, then the web applications can use that. Sometimes also people refer to that term. I just wanted you to be familiar with the term of Web of Things. In IoT, most of the time you're talking about Internet of Devices, they are connected to each other. When people use that terminology now, they refer to Web of Things. Most of the time they are referring that data or those services are available at the web level, means at HTTP or application level they're available. Just I wanted you to be familiar. Sometimes you come across the terminology of Web of Things. Based on what we have learned, if you want to create a Web of Things platform, for example, you can create gateway models. You can write components which can act like gateway. You can use protocols like CoAP, or you can use protocols like MQTT. And then you can create backend servers which supports HTTP communication, and the rest is just web programming. You basically make your data available via MQTT and a message bus, which we discussed last week, and you publish your data, and then you write web applications which can take and use that information. Or you can write like HTTP, CoAP-based data communication, or you have very low-level data in different IEEE 802.15.4, and use a gateway which communicates with the network device from one side, and the other side has HTTP communication. If we want to use our XM1000 devices to basically make our data available on the web, what are we missing? How do we create that gateway? Yes, we need a gateway. How do we create that gateway? That gateway needs to have some sort of 802.15.4 radio to be able to talk to our XM1000, and from one side needs to have, let's say, Ethernet or Wi-Fi connection and HTTP support. And as long as if we have a device which from one side can communicate with 802.15.4, probably we can get, and the other side we need to write a web-based application to be able to publish that data using RESTful services. In principle, you should be able to take one of your XM1000, plug it into a computer, you write a program to read that data from a USB device. Saying it's much simpler than doing it, I know, but in principle you can create your own gateway with one extra mode to be able to do that. There are a few things, again, semantic technologies. Most of the existing IoT solutions or most of the practices you have done so far in your lab is relying on syntactic solutions. It's syntax-based, CSV-based, comma-separated format sending data. If you use XML, to some extent you're supporting interoperability, but what we said is tree-based structure, being able to link the documents based on meaningful relationships, and agreeing on terminology exists. And then if you add semantics, you can start addressing some of these limitations, and you can integrate data. Creating semantics will allow us to create machine interpretable information. That doesn't necessarily mean machines will understand that. Still, you need to write high-level logical rules or descriptions. We can process and interpret the information, and also can automate the process. Again, the more machine-readable, machine-reusable information you create, the more automated the process becomes. Like, again, going back to our example of creating a common language for medical devices to be able to send data, then your back-end systems, your software agents, they don't need to manual, say, setting or programming to be able to read data. You just plug a device, and as long as the devices send information using a common ontology, a common language, your system picks up that data and uses it. What are the key challenges? Then back to our very early question, why don't we have really global ontologies? As I said, it's easy to explain. It's difficult to make people interested in coming and using your ontology unless you have created a big community behind it. And also when you create description frameworks, usually these description frameworks are a starting point. Still, you need lots of tools and libraries to make them actually be able to use that data. Often when I see people create ontology or data models, people create the model and expect somebody else will come and write the tools. Somebody else will come actually annotate that data. And often that limits the uptake of the ontology or data models. Once you create a model, you also need to create tools to allow people to come and use that data. You need to show cases, use cases. You need to have a platform probably to support integration of that data format. Once you do that, you basically, your ontology or data model you have created will have higher chance of actually being used in a real world. In our case, for example, when we created the ontology to describe the medical data, we had also a platform behind it which provided libraries for third parties, like we have, I don't know, Python libraries, Java libraries, different libraries. If you have a device, we give you the library, you supply with comma-separated data, we create the data according to our format. We have a platform which you can integrate this data. We have validators which you can validate data against your description. Then you have all the basically the data flow to actually to start from the source to integrate your data into a platform. It's not just the modeling is one part of the work. It's not the only answer to the problem. And then there are different tools to create this RDF descriptions to validate them. One of the very famous tools, if you are interested, again, in this module, we won't focus much on it. Next semester in mobile applications and web services, we'll study this more. But there is a tool called Protege. Is an open source tool. If you want to create like RDF-based ontologies or OWL-based descriptions, you can use that. You need, again, to decide what terms you're going to use, how that common those terms you are using in the community people are going to use, how you those terms are described, what are the relationship between them, and providing again complementary tools for allow people to be able to use those annotations and integrate it into their programs. In IoT, try to avoid using complex models, create more modular models. Again, focus on the problem. If you're designing an ontology, or if you're designing a semantic model to describe your metadata, you're addressing a problem, and where that problem is, why in the first place you wanted to do that, and look at the common terms. What common terms are used in that domain, and as much as you can, link your data to other resources. Some of this you will find them when you really do practical examples. If when you're building a platform, and in most of the platforms, if you really design a proper IoT system, you need to address this problem. Otherwise, your platform will work within your domain with the devices you are using now, and tomorrow if you want to add a third-party device, again, you need to reconfigure it, reprogram it. Then lots of these steps are important for real-world cases. I'll leave it this to you, but uploaded the description. I think this is, again, in example, I will ask something similar to this. I will give you a description, and I will say, if I have a sensor which measures this information, use a graph model, use a triple description, and create an ontology to describe something like this. I've uploaded the solution for this both in JSON and XML format. Well, we have 5 minutes. Let's try that. Have a look at this for a minute and tell me how this ontology will look like. Okay. I'll start. Can I say we have a concept which is observation and measurement data? That's the first part. We have observation and measurement data. My observation and measurement data can be two types. Can be environmental monitoring data or it can be physiological. Is that correct? Can I say this environmental data is measured by? I'm going to call this medical device. Right. That now will create, I have a body temperature sensor and I have ambient temperature sensor. I take this too. I created this. Right? And can I say ambient temperature is a part of temperature? Let's say, call it data. Can I say ambient temperature is part of its type of? Is that temperature, is an environmental temperature? Can I say body temperature is a? Physiological measurement? This will be now my abstract level. I've created just the abstract concepts to say I have observation measurement data. My observation measurement data has two categories, either is environmental or physiological data. Within this physiological data and environmental data, I have ambient temperature, which is environmental, and I have body temperature. You might use a different modeling to create them.
The actual temperature of the ambient device, because you can have multiple devices.
So sorry, I didn't get the
actual data that the ambient device.
actual data, this data itself, this one, you mean?
It means that the ambient temperature is measured by the device. The ambient temperature is an environmental data, but something else can be measured. In that sense, it only measures ambient temperature from the solution.
Oh, here, you mean that the device can only measure the environmental temperature?
Yeah. Ambient data should be connected to the device because you have multiple devices that measure different.
Haven't started that yet. I haven't started that. That's correct. Yes, that's a valid point. Still, there is no connection between my. That's the correct point. Still, there is no link between my device and data. Can I say, for example, my device measures, for example, virtual data, or I might remove that and I say I have a device which is called ABC001, whatever it was called over there, whatever, AB23. Let's just use the same thing. And I say measures this, measures ambient temperature. Can I write it this way? This is now my instance level. This was the green ones are my abstract levels. This is my instance level. And by doing that, and now I can ask a question, for example, find me all the sensors which they provide environmental data. And the machine can go and say, ambient temperature is a type of environmental data, and this sensor measures the ambient temperature. Then this sensor is also measuring environmental data for me. Then basically, your machines can be able to find some implicit information, some indirect information which are not explicitly defined for machines. You can write rules to go and explain that. Can I create another device here? What was the device name? 123 AB23. 123 AB23, and say this device measures body temperature. And now I can say, go and find in this domain all my physiological or medical devices and tell them what they measure. In our medical case domain, in the real applications, we needed to go and check to see if we have collected data from all our medical sensors on a daily basis. Then I could just write a program to say, go and find all the descriptions which are physiological data, find all the devices that are collecting physiological data, and then go and see whether I have to get the data description. I've collected data. What it solves, if I have now 3 medical devices today, I'm only measuring blood pressure, body temperature, and say pulse. Tomorrow, if I'm measuring device number 4, I don't need to change my backend software, because my backend software will always go and find first all the physiological data, will find all the devices that measure physiological data, and then we'll start looking for data. And if I introduce a new device to my domain, what I only need to say, I say this new device is a physiological monitoring device. The rest of your, basically in common language, you describe it using common language, most of your backend software to analyze that data will stay the same. Is that clear how that actually is semantic and modular description allows you to create more flexible and scalable structures?
What's below the physiological?
Sorry, I didn't.
What's below the physiological?
Below the physiological data here.
Yeah, what's that say?
Sorry for my bad handwriting. That's called, oh, let me use the same color because the color scheme here has a meaning. Medical device. Again, these names are conventional. I use the medical device. You could touch it with a touch.
What's the colour scheme again?
The green ones are the schema abstract concepts because they are not, and the red ones are the instances. Show the schema in green and instances in red. Two more examples of use describe this as JSON and XML. I've uploaded them online. They're on SariLearn and you can find them. Any questions? Again, as you can see, most of this semantic descriptions are really simple. There is no really complex description. The notations mainly are based on XML, syntax-based notations. The important thing is finding the best way to describe, creating the common ontologies, using common vocabularies, and designing methods and approaches which to make this data annotation easier for third parties to use, and creating tools which can integrate data coming from different formats. Once you do that, you're getting closer to create more interoperable formats. Think of if you want to add some interoperable format or some metadata description to your assignments. When you are reading your data, analyzing your data, you're generating fire, create that fire using a description, a semantic description. Tell me where that fire is originated from, what is the location for it, what is the time for it, and I don't know, what was the original values which you thought are fire, for example. Just giving some idea for your assignments. Okay? See you in 10 minutes in the lab.